Sarah's quite a character, isn't she?
Yeah.
So I'm sure a couple other people will be coming in a minute or so here. So I'm, again, like last time, not going to keep you very long tonight. We got just one more thing to do, and it's the integration I told you about. So I'm going to give you sort of a quick rundown of how the integral for polar comes about. And it's directly related to the, whoops, let me start this, I forget. I'm just going to do like 2.5 examples tonight. So the integration is going to pull us back to chapter 8 a little bit, some of the trig integrals, power reducing formula, and that's going to bring us to the end of Calc 2. So I'll send out some homework on this. When we're together next Tuesday, we'll go over any of the homework problems you want from chapter 10. I'll be sending out some questions about that, just like before. You write them up, you mail them back into me, and that will be the end of the Calc 2. So, and I'm sorry, I don't have the test grades up yet. I was kind of out of it for a few days. I got some sort of, not COVID, I got some sort of thing that kind of kept me horizontal for a couple of days. So I'll try to get those grades up. Well, it's going to be too late tonight. I'll get them up tomorrow because I have nothing else going on. Before we get started with integration stuff, anybody got a question about anything? Anybody good?
Number 65 on the homework, the vertical tangent lines.
Okay, so let me see, number 65. So for vertical, you're looking for the denominator to be 0. That's where, and that's where that comes up. Let me just find that page in the book here. 65. We are 65. So we have. And I cut and paste the formula in because I kind of goofed that off. I was not feeling so hot last class, and I kind of goofed that formula up. Fortunately, a couple of you were right on top of it and caught me on that, which I'm very grateful for. So we have f of theta cosine theta plus f prime of theta sine of theta, and then we've got let's see here. Negative f of theta sine theta minus f prime of theta cosine theta. Okay, so that's the formula as written in the textbook. So if we're looking for vertical tangent lines, so for a vertical tangent line, what we're looking for is that to be 0. We're looking for a 0 in the denominator, but not a 0 in the top. That's a different thing that happens up there. So number 65, see if I can read this book here. Hang on a second. 65. So 65 is r is equal to 1 minus sine theta. Did I do that right, John? Is that the correct problem? 1 minus sine theta?
Sorry, yes, it is.
Okay, so we'll put it into here. So I'm only concerned about, well, we'll do the whole thing anyhow. Whoops. So we have on the top, so f of theta, so instead of r, I'm going to replace that by f of theta. Same thing, different notation. And we put that up here, 1 minus sine theta times cosine theta plus, now the derivative of this, derivative of 1 is 0, derivative of negative sine is negative cosine. So that will give us negative cosine theta and then sine theta. So there's the top of the derivative. The bottom is negative f of theta. So we will do negative 1 minus sine theta times sine of theta. And then minus, so our derivative here, so now we use the derivative again. The derivative is negative sine. sorry, the derivative of negative sine is negative cosine. That changes this to plus. And then we have another cosine over here. So there's the full derivative. dy dx is equal to that. Now, this problem asks for vertical. If we wanted a horizontal tangent line, we would set this to equal to 0. If we want a vertical tangent line, we just set the bottom equal to 0. So that's the concept behind all of this. So I'm going to multiply all of this out. So this gives us just the denominator. We multiply this out, we get -1. So we get, oh, sorry. I multiply all this out, we get negative sine theta, and then we get plus sine squared theta, plus cosine squared theta. So this negative gives me -1 times sine is negative sine, negative, negative, positive, sine times sine, sine squared. And sine squared plus cosine squared is equal to 1. So the denominator of this problem now becomes, so now we have, and we want all of this to equal 0. So this gives us negative sine theta plus 1 is equal to 0. So that gives me negative sine of theta is equal to -1, just a little bit of algebra there. Negatives cancel out, and sine of theta is equal to 1.
Just to let you know, the second sign in the denominator for the calculating the derivative was a plus instead of a minus.
Wait a minute here. So what did we have? We had 1 minus sine theta, and then we had plus cosine squared theta. Is that what the denominator was?
Yeah, but that was with making the one cosine negative. I think the signs might be flipped.
So
Not sure though.
is this part right?
Yeah, that part's definitely right.
Okay, because wait a minute, hold on. I gotta let Mariana in here. Hang on, somebody's coming in. Because I erased it and I didn't quite. So we're good here. So this is the next part, right? All right, so let's multiply. Maybe I made a mistake multiplying it out. So we multiply this out. We get -1 plus sine theta times sine theta plus cosine squared theta. So what I did is take the -1 into these parentheses here, right? And so that should give me negative sine theta plus sine squared theta plus cosine squared theta. I think that's what I had before. Have I made some kind of mistake and I'm not seeing it?
I'm sorry, is this the plus cosine squared would I think it's negative cosine squared because the formula that you used to find the derivative, I think the one was a negative instead of a positive, which I did on my homework, by the way, so.
Well, so in the formula, this was a negative, but when we do the derivative of this, we get negative cosine, and that changes that to a positive sign.
It's just in the textbook that's positive.
What's positive?
The second sign, so it would be flipped to negative.
Hang on a minute. Let me start again. So I'm looking at the bottom. I'm looking at the bottom of the derivative. Negative signs. They've caused trouble ever since you were introduced to them in like 5th grade, haven't they?
I hate them so much.
That's why I get rid of them as soon as I possibly can. So let me look at this. Hang on just a second. So I'm only looking, so dy dx. I'm only looking at the bottom here. That's all we're concerned about here. So we have negative f of theta, and then we have sine theta. And then we have plus f prime of theta, f prime of theta cosine theta. Okay, whoops, there we go. All right, Now this derivative, so f prime of theta is negative cosine theta. So now we put this in here. So it's negative the function. So we get on the bottom, we're just looking at the dx part here for this problem. So we get negative 1 minus sine theta times sine theta. And now plus, now the derivative is negative, so that changes this to a negative cosine theta times that cosine theta, which gives me cosine squared theta. Ah, is that? Oh, there it is. And I had a plus there before, didn't I?
Yeah.
Ah, there it is. I got ahead of myself. Okay, so now we have negative sine theta. Then we have plus sine squared theta. And then we have minus cosine squared theta. There we go. Is that correct?
That's where I got. It's just I don't know how to make that solve that for 0 without things getting all wonky.
Yeah. So there we are. So there's a couple of things you can do here. So the thing is, so sines and cosines are transcendental functions. They are not algebraic functions. So you can't solve this by normal, you can't solve this by sort of normal algebraic means. But we can change the cosine squared into a sine squared, can't we? Because we know that sine squared plus cosine squared, is equal to 1. So cosine squared of theta is equal to 1 minus sine squared theta. So we can replace this by this and taking into account negative sign. So we're looking for 0 is equal to negative sine theta plus sine squared theta. And now I want the negative of this. So I'm going to get plus sine squared theta minus 1. And this now leaves me with 2 sine squared theta minus sine theta minus 1. Are you okay with what I did there, John?
Mm-hmm. This is where I got.
So if I say the phrase U substitution to you, what do you think of because you're in Calc 2? You think of U substitution for integration, right?
You can use it for simplification too.
And if you remember pre-calc, so I'm going to do a different sort of U substitution here. Not a calculus U sub. U sub, even in calculus and algebra, U substitution is just a visual trick. So what we have here is 0 is equal to 2u squared minus u minus 1. So I'm just replacing the sine theta by the letter u, so that visually now what we see is, oh my goodness, it's a quadratic equation. And how does this factor? Well, they all factor, but does this factor nicely? So we would have 0 is equal to, so 2u and a u, right? And then we would have a minus 1 here and a plus 1 here. Are you okay with that?
That makes sense.
So you
I didn't even think about that.
Yeah, well, yeah. So, well, you probably wouldn't, because a lot of folks have never seen this U substitution. Doesn't mean just integral. It's just a visual trick to take something that looks complicated and it's say, oh, it's just a quadratic equation, right? Because now, in fact, I could have put 2x squared minus x minus 1 here. So now we can factor this thing. So looking at that should be a 1. So now we have 2u plus 1 is equal to 0, or we have u minus 1 is equal to 0. So this says that u is equal to negative 1/2, or u is equal to 1. And what we did, we let the sign be u. So we're looking for the sign is equal to negative, sine of theta. Sine of theta is equal to negative 1/2, or sine of theta is equal to 1. So over here, theta is equal to pi over 2. And over here, theta is equal to the arc sine of negative 1/2. And for that, you need a calculator and make sure that you're using radians. Well, actually, you probably don't need a calculator. So when the sine is equal to 1/2, you're looking at pi over 6, but because of the negative sign, but you could use a calculator for that. So does that help with that problem?
Yeah, that helps a lot. Thank you so much.
Yeah, no, that was a good one to ask. I kind of like it when you ask that because I don't really do these ahead of time. I pick out homework problems because I kind of know what I'm looking for, but I don't actually work them out so much. So that was a good one. Glad you asked that. Anybody got anything else? Good thing these are take home, isn't it? Well, all right. So let's finish up the new material for Calc 2. I'm going to do 2.5 examples tonight. The half example is I'm going to take you almost all the way through it. I'm going to leave it for homework on you. So let's go back to a little review from Calc 1. So tonight we're going to do area. In Calc 1, area was generally its area under a curve between a curve. So when you were introduced to integrals somewhere towards the end of Calc 1, everywhere in the world introduces an integral the same way. They do it in terms of geometric area. So you have some function that goes from A to B, and you have some function, and you want to know the area of this odd-looking shape. So you do so we have an interval here from A to B, and you partition that integral, and then you make these into rectangles. And you can make your rectangles under the curve, over the curve, halfway. There's some things on there. If we make all of our integrals the same width, each rectangle has a width of dx. We calculate the height of each rectangle using a finite series. And we calculate the area of each rectangle, add them up, and that gives us an estimate of the area of that weird looking shape. Then in calculus, what we do is to make the estimate closer to the true value, we make the rectangles skinnier and skinnier and skinnier and put more and more rectangles in there. That makes the little error area go away. And to find the exact error, the exact area, we use the concept of a limit. Those rectangles shrink down to 0. Now we have an infinite number of rectangles. It's the exact area. And so our area becomes this. From A to B, the integral of f of x dx. So this s, this integral sign, the integral sign just really means an infinite sum. We have an infinite number of rectangles and we're adding them all up from n equals 1 to infinity. And because this is like a philosophical leap, we go from the Greek letter S to the Old English letter S. So that's the idea. And the moral of this little analogy here, we are using a geometric object over and over and over again. Rectangle, 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 rectangle. We're going to do that tonight with a polar function, but we're not going to use rectangles. We're going to use sectors. So let me remind you what sectors are. Something you should have seen in pre-calc, and I know that some of you haven't, and I know that some of you have, but don't quite remember them. So a sector that's a sector. It's a section of a circle with a point on here. Think of pizza pie slice. A sector looks like a slice of pizza. It's a chunk of a circle starting at the center and going out and having that curved edge on the pizza crust. And so we have an angle. So theta, and by the way, for these problems, if there's a point at which you need to use calculators, make sure you're in radians. It's important to be in radians because we're dealing with geometric objects here and length and distance. And a radian is an actual real number. A radian is a number that's on the x-axis. So pi is at the x point 3.14 roughly. Degrees are not actually numbers. If you have 45 degrees, that's just the name of an opening of an angle. A radian is an actual real number. You can measure it with a ruler. 2 pi inches is 6.2 inches roughly. I can hand you 2 pi worth of Cheerios. If I say, how many Cheerios do you want? And you say, I'll have 2 pi. I would give you 6 Cheerios and a little crunch of another one. If you said, I want 30 degrees of Cheerios, I can't give you any Cheerios because that number 30 isn't actually a measurable number. So theta is in radians, and the distance of this side is r from here to here. And the length of this on here, called a chord, we use the letter S. So that's our pizza pie slice. And here, S is equal to R times theta, when theta is in radians. If you know the radius and the angle, it will give you the length of the crust of the pizza. And the area of the sector is pi r squared over 2. That's the area of a pizza pie slice. And instead of rectangles for area, we're using sectors. We're going to divide everything up into pizza pie slices, and then we're going to integrate on here. So I'll show you a quick little diagram of how that works. If we have a polar function, so we have this polar function. So let's say this is f of theta. And we want to know I want to know the area of this shape, which is pizza pie-like, but we have this weird curve on the end. Just like when we do functions in calculus, we got the x-axis, but then we have this weird curve going above it. So from here to here, this is our first angle. So this is theta is equal to alpha. So when we do it from Calc 1, from Calc 1, we integrate from A to B for the area of the shape. So alpha is the first letter of the Greek alphabet, so this is basically A, but we always use Greek letters when we're talking about angles and things. It's because of the Greeks. And we come over here, here's another angle. This is where we stop, so theta will equal beta. So instead of A to B, we're going from alpha to beta. To figure out this area, we make everything into rectangles. And here, we're going to make everything into slices. There's a sector, there's a sector, there's a sector. So to estimate that area, we can figure out the area of each one of these sectors and add those 3 areas up. That would be an estimate of the area. To make that estimate better, we just throw in some more sectors. Now the area is more and more accurate. And what we do is we let the angles here, we let theta go to 0. And that will give us the exact area. And we're going to call this, we let d theta go to 0. So over here, all of our rectangles have width dx, and we let dx go to 0 to get the exact angle, or the exact area. So the analogy here is just the same as you saw in Calc 1, but we're not using rectangles, we're using pizza pie slices. So to integrate from a beginning angle alpha, and we let theta change all the way up to here to beta. So to get that area, we integrate the area up here. And the formula that we come up with is the area is 1/2, there's the 1/2, from alpha to beta, r squared d theta. It's the angle that's changing. So here's r squared over 2. Here's r squared over 2. The angle is constantly going a variable. So theta takes the place of x, and it's changing. So we have d theta over here. And the other alternate to this is just a change in notation. It's or 1/2 alpha to beta f of theta squared d theta. Whoops. So the only difference here is r or f of theta, but they're all the same. So that, in about 3 or 4 minutes, is kind of the theory. It's exactly the same as Calc 1, but instead of rectangles, we're using sectors. Concept is still the same. It's a repetitive geometric object, and using the concept of a limit, we shrink that thing right down to 0, so we have an infinite number of them in there. So there's the theory. The book has some nice pictures in here. In fact, if you look up, you'll see nice pictures all over the place of this thing. All right, good so far? So now I'm just going to do a couple of examples. So here's our first example. Okay, scene 1, this is kind of a scene 1, seen them all sort of thing. Where's my example? Here we go. All right. R is equal to the cosine of 2 theta. Now draw a very bad sketch of what this looks like. So this looks like this. Well, it doesn't really look like that at all. Hang on. It's basically a perfect 4-petal flower. So as theta goes from 0 to 2 pi, we get this 4-petaled flower. If this was not a 2, but a 4, there would be 8 petals here. If this was a 6, there would be 12 petals here. However, if this is an odd number, if this was a 3, there would only be 3 petals here. And there's pictures of these in section 10.4. The problems we're doing tonight are section 10.5, but your TI-84s draw these pretty nicely on here. So if we wanted to find out what's the area of all 4 petals, we're going to take the lazy way out, because being lazy is good in math. So in order to figure area, we're going to take advantage of symmetry. We're going to look only at the half of the petal in the first quadrant. We're just going to look at the area of that half petal. So if I wanted to know the area of everything, I just would multiply by 8. If I wanted to know the area of 1 petal, I would multiply by 2. So right here, this is theta equals 0. If theta is 0, 2 times 0 is 0, and the cosine of 0 is 1. That will put r right here. The next angle coming up here is theta is equal to pi over 4. If theta is pi over 4, 2 times pi over 4 is pi over 2, and the cosine of pi over 2 is 0. So that graph comes right back down into the origin. So here's our alpha, here's our beta. And to do this integral, Now it's going to feel like we're all the way back in chapter 8 again. So our integral becomes the area of that half petal is 1/2 from 0 to pi over 4, the cosine squared of 2 theta d theta. That will give us the area of that half petal, or half petal. So the only thing new tonight, really, this just looks like a problem from chapter 8, which probably seems like 5 years ago by now. The only difference now is we're giving this integral a geographic meaning. So that's really all that's new tonight, is what does this integral actually tell us geometrically, and it's that area. So let me just pause there for a second and see if anybody's got a question.
How'd you get that top bound again?
Because I know the answer. So that's a smart ass answer. The tricky part in here is coming up with those angles. On the homework, I'm going to give you the beginning and ending angles. So I know.
Okay.
So let me enlarge this. So the x-axis is theta equals 0. When theta is equal to 0, 2 times 0 is 0, cosine of 0 is 1. So that puts r right here. Now, if I draw this, so here's theta is equal to pi over 4. So at pi over 4, 2 times pi over 4 is pi over 2, and the cosine of pi over 2 is 0, so that puts me here. So between 0 and pi over 4, so if we start plugging in all of the angles from 0 to pi over 4, what's going to happen is these are going to be our R values. You'll get all of these over here. So I like to think of these graphs as these little dots are the airplane, and the origin right here is the airport, and these are the radar beams going out and hitting that airplane as the angle changes. So what happens is it will draw out that top half of the petal. Does that kind of help a little bit, Jordan?
Yeah, that makes sense. Thank you.
I think, I haven't looked at TI-84 in a long time, but when you graph these on a TI-84, I think you actually see the graph being drawn. You'll actually see those lines. It doesn't just pop up as a graph. You'll kind of actually see that black line being drawn. So that's kind of a good thing to check out. So the answer is, I knew that the curve goes back to the origin here, so I knew it was pi over 4. When I send out the homework, even though the homework doesn't give you the angles to start and end at, I'm going to give you the angles to start and end at. Coming up with those angles is like an entire class all in itself, and describes it in the book a little bit, but that's kind of not what we're about here. Okay. All right, so now forget this. Forget all this. Put your minds back in chapter 8. How do we do that integral? What method do we use to do that integral? Can't be a u sub because there's no sign. So what you're going to find out a lot in a lot of the homework problems is we go back to our friend power reducing, where the cosine squared of x is 1 plus cosine of 2x over 2. Does that ring a bell? You kind of remember seeing that a little bit? Oh, Derek, I didn't notice that you had the answer up there. Nice job. I got to remember to turn my head more and look at the chat stuff over here. Now, I'm using an X here to remind you that whatever this is, you double it. So we're going to apply this to here. And that will mean our area is 1/2 0 to pi over 4, 1 plus the cosine of 4 theta, all over 2 d theta. So this is 2 theta. The formula says to double it. That gives me 4 theta right there. All right. Now, this 2 is just a constant, so I'm going to take the 2 out and put it over here. That gives me a 4. Now I don't need this line anymore. And now to do this integral, we get 1/4. The integral of 1 d theta, the integral of 1 is just theta, plus the integral of cosine. Is it positive sine or negative sine? We're doing the integral of positive cosine. Do we get negative sine or positive sine?
Positive.
Yeah, positive. That always causes a moment of pause, doesn't it? But we need a little tiny u substitution here. So we're going to get 1/4 the sine of 4 theta. And then we go from 0 to pi over 4. So forgetting this part for tonight, this is just a chapter 8 trig integral. And the last step is to plug numbers into here. All right, I'm going to pause if anybody's got a question. So this is pretty much familiar from things. It's been a while since chapter 8 because we had all that sigma series stuff. The only difference again is now we have a geometric interpretation of what this integral is telling us. So now we put our numbers in. And so the area is 1/4. We put pi over 4 in for theta. Put pi over 4 in for theta. 4 times pi over 4 is pi, and the sign of pi is 0. Then we do minus 1/4. We put 0 in. 0 here gets 0. 4 times 0 is 0, so we just get another 0 here. And our answer is pi over 16. That pi over 16 unit squared, that's the area of just the top half of that petal. So if I wanted the area of the whole flower, there are 1, 2, 3, 4, 5, 6, 7, 8. I'd have to multiply this by 8, and we'd have pi over 2. If I wanted just the area of one petal, we'd multiply this by 2, and that would be the area of each petal because they have perfect symmetry here. All right. We got questions about that? So kind of familiar, right? So it's nothing all of a sudden. So far, our last lecture of the semester, at least as far as stuff goes, it's new, but it's also not new. It's something you've already known. It's just a different interpretation on that. All right, so I'll do, that's the first example. I'm going to do another example and then half of an example, and that's going to be it for us tonight. Okay, so I'll do this next example now. Am I recording? Yes, I am recording. Next function. R is equal to 4 sine theta. So there's our function, 4 times the sine of theta. Here's what this looks like. Well, it doesn't really look like that. Hang on. Oh, that's much better. That equation is a circle sitting on the top of the x-axis with the y-axis going right through the middle. And we're going to do the area of half of it. So our first theta is 0. If theta is 0, the sine of 0 is 0. 4 times 0 is 0. That puts us right here. If theta is equal to, hang on just a minute. Pi over 8. Nope, that's not what I want. Pi over 2. The sine of pi over 2 is 1. 1 times 4 is 4, and that puts us right there. So we're going to start at angle 0. We're going to let the angles range all the way up to pi over 2, and it will draw that half circle right there. So to figure out the area of the half circle, it becomes area is equal to 1/2, 0 to pi over 2. And we square this, so that gives us 16 sine squared theta d theta. $16 is a constant, we pull that out. So 1/2 times 16, that gives me an 8. And my integral now just becomes sine squared. And if you look over in the comment section in the chat box, Derek already has the answer for us. We're going to do power reducing again, but this time it's sine. So sine squared is equal to 1 minus cosine, sine squared of x is 1 minus 2x over 2. So this now becomes area is equal to 8 times 0 to pi over 2. And we get 1 minus cosine of 2 theta, because we've only got 1 theta here, all over 2, and d theta. And I'll pause there in case somebody's got a question. Oh, by the way, this problem is number 1 in section 10.5. It's the first homework problem. This is number 1, and we're on page 731, section 10.5. But you'll be getting a picture of that later. Okay, now this 2 is a constant. I can pull this 2 out. 8 divided by 2 is 4. And that leaves me with this. Same as last time, except this is not a positive, this one's a negative. So our area becomes 4 times the integral of 1 d theta is theta. We have a little u sub here. The integral of negative cosine is negative sine. So we get negative 1/2 sine of 2 theta. And we're going from 0 to pi over 2. And other than doing the arithmetic, this problem's pretty much done. So I'll pause for a question. Also pause to clear my throat a little bit. Anybody good? Okay. So we put pi over 2 in here. Pi over 2 for theta. Theta is pi over 2. We put pi over 2 in here. 2 times pi over 2 is pi. The sine of pi is 0. So we just get 0 here. And when we put zeros in here, we get 0 again. So our answer is 4 times pi over 2. So our answer is 2 pi. So 2 pi, our answer here, that is the area of the right half of that circle. Questions, comments? It shouldn't seem too bad. Well, depending on how your relationship with chapter 8 was and the trig stuff. Now, there was an easier way to do this problem, by the way. We could have done this problem without calculus. This is a circle. This is the point 0, 0. Right up here, this is the point 0, 4. And here's the middle. So the radius of this circle, is 2. The area of a circle is pi r squared. So for this circle, the area would be pi 2 squared. The area would be 2 squared is 4. The area of the whole circle is pi 4 times pi. Half of the area is 2 pi. Oh, yeah, Brandon, I'm going to give you the angles from where you start and stop. The book has some explanations in there. Explanations are not really good. I'm going to give you, for the homework problems I assigned to you, I'm going to give you the start and stop points. I know when theta is equal to 0, sine of 0 is 4. That puts me right here. So when theta is 0, r is 0. So that gives me this point 0, 0. When theta is pi over 2, the sine of pi over 2 is 1 times 4 is 4. So we get this point right up here. But I'm going to be giving you those. So here's geometry of the whole circle. We just did half the circle, and half of 4 pi is 2 pi. So that your intuition should be okay on those.
I have a question.
Yep, go ahead, Michaela.
So you know how, like, sometimes when we're doing integrals, if like there's a negative part, like it's not going to give you the area, like the total area, because it's going to subtract the one part.
Right.
Do you want us to give you the area or the integral? You know what I'm saying? Like,
Oh, so integration can give you area, and the other one you're talking about that includes negative numbers, that's called displacement.
okay.
Let me go back to this other function. That's a great question. The homework from chapter 10 is only area.
Okay.
If you come out with a negative number, you made a mistake. If you come out with 0, you probably made a mistake. Let's go back to that first function of ours. That's a great question. So here is r is equal to cosine of 2 theta. So what we did before was we went from theta equals 0 to theta equals, what did we go to here? To pi, I think we went to pi over 4, right? Yeah. That gave us the area of the top half here. What do you think would happen is if we went from 0 to 2 pi? If we went from theta 0 all the way around to 2 pi, what do you think our answer would be?
0.
It would be 0. Excellent. Why would it be 0?
Because all the like halves would cancel each other out. Like the top half would cancel out the bottom half.
Yeah, exactly. Because even though my drawing doesn't look like this, it's perfect symmetry. The area of this flower above the x-axis is exactly equal to the area below. Area above the x-axis is positive, area below is negative, and the answer would be 0. That's correct. And that could be the right answer depending on how the question is asked. If you're asking for total displacement, so if you start here in the morning and you drive all day long, you drive all the way around, and at the end of the day, you come back here. If you start at home and you end up at home, your total displacement is 0, right? But in this section in 10.5, we're asking about actual physical geometric area. So your answers have to be positive. And that's why to get the whole area, we would have to break it up. That's an excellent observation, Mikhail. Okay, so far so good. This really isn't so bad, right? All right, I'm gonna do one more example. I'm only gonna get you started and I'm gonna let you do that, finish it for homework. So here is our last example for tonight. Oh, this is our last problem of the whole semester. How's that feel? So last problem of the whole semester. Tuesday's just review. So we have R is equal to, let me make sure I write the right thing down. 1 minus cosine of 2 theta. This is actually number 4 in the homework sheet for tonight. It's an even one, but I'm just going to get you started. And here's what this looks like, sort of. This is, well, not quite. That function graphs a vertical infinity sign. So if we wanted to do this area, well, we're going to do this part right here. Now, when theta is equal to 0, if theta is equal to 0, that puts us right here. If theta is 0, 2 times 0 is 0. Cosine of 0 is 1, and 1 minus 1 is 0. So that puts us right here. And now I want to be up here. So now I'll let you think about this one for a minute. What angle is going to put me up here? I need to make this disappear. So if we have pi over 4, if theta is pi over 4, 2 times pi over 4 is pi over 2, and the cosine of pi over 2 is 0, so that gives us 1, and that puts us right up there. So, Brandon, even though I'm going to give you the start and ending angles in the homework, my little verbal thing there is no rule for doing. You kind of got to think about it a little bit. You got to decide, where do you want to start and what angle will put you there, and where do you want to end and what angle will put you there. So there's like thinking going on there. All right, so there's a setup. Yeah, so the book does some examples, but it's tough to read a math book. Reading a math book requires its own skill set. To really be able to read a math book well, you have to already know what it's saying. And it sounds crazy. So in some ways, so Kayla and I, who are here to help you, our job in some ways is to be the go-between between you and the book. So the book is speaking in like official doctor lawyer language, and Kayla and I try to humanize that for you a little bit. So yeah, it takes a little bit of practice. For those of you going into Calc 3, these are polar coordinates. In Calc 3, you're going to get other sorts of three-dimensional coordinates. You're going to get something called spherical coordinates, where all your geometry happens on the surface of a basketball or a bubble. And there's certain ways to calculate distance and length and area and volume and all that. You'll also have something called cylindrical coordinates, where all of your geometry happens on a column. And polar, yeah, Brandon, polar comes up in Calc 3. Yeah, it does. Yep. Because we've seen from the first time we did it, converting something into polar coordinates, if you looked at that slideshow at all, takes a horrendously awful looking XY equation and turns it into something just relatively simple with polar. Okay, so final thing, I'm just going to get you started on this. So the area is 1/2 from 0 to pi over 4. And then it's 1 minus cosine of 2 theta, that whole thing squared. d theta. So the only real difficult part is coming up with those angles, but that's not a calculus thing. That's going to be fine. So now the question is, how do we do that integral? How are we going to do that integral? Well, how are you going to do that integral? I already know how. What do you think? See, back to chapter 8. So Derek, good idea. What would you let u be? If you want to do a u substitution, what would your choice for u be? Oh, well, yeah, eventually we're going to have to do that. But what about this? This is the problem up here. It's this thing that's the problem. This is a u sub here. The integral of negative cosine is negative sine, but this little bit, that 2, means you have to do a little u substitution in there. But what are we going to do about this square that's outside the parentheses? That's the bigger issue.
Would you like multiply it out and then use power reducing?
Yes, both of those things. The way to do this is this is what I meant by 2.5 examples. So the way to do this is like Michaela said, we're going to multiply that out or expand it or distribute it or unfoil it or whatever your words are. So we get a is equal to 1/2, 0 to pi over 4. So we multiply this out, we square it, we get 1 minus 2 cosine of 2 theta plus cosine squared of 2 theta d theta. And that's how you do that problem. You had to actually multiply it out. So now we're ready to integrate. So we're working d theta. So this is going to be theta. Here's the little u sub that Derek was talking about. So this is going to be negative sine of 2 theta. And this one over here will be power reducing, which is exactly what we had on the very first example tonight. It was the cosine of 2 theta, so you just follow that. And then when you're all done, you plug in the zeros and the pi over 4s. And that will give you the right half of the top pedal. And then if you want the whole thing, you'd multiply by 4. If you want one pedal, you multiply by 2. That's just trivial stuff at the end. And thus endeth Calc 2 for this semester. How about that? We all made it. So questions, comments, anything like that? So I'm going to send out some homework. And not a lot, 4 or 5 problems or something. So over the weekend, because I know all of your other courses are, slamming you pretty hard right now because there's only a few days left. So this is kind of a little lightweight thing at the end of our semester. And for those of you going into Calc 3, the things I've shown you in Polar are the kinds of thinking you're going to need when you hit that cylindrical and spherical coordinate stuff. So on Tuesday, we'll review anything you want from chapter 10. And after that class, I'm going to send you out some questions like before. And they'll be due. So the last day of the semester is Wednesday. Yeah, it's Wednesday. So it'll be due by then. Kind of same old routine we've been doing all along. So who's got what? Questions, comments, anything you want? Didn't I put the last, you know what? I totally, I almost said the F word. I totally messed up. The file from last class got corrupted or something. It's not there. But the file from last class, so in the homework, I put the formula for the polar derivative. So you just follow those. That last class, I don't know, I hit the button wrong or something. So right before, I was feeling kind of crappy. I had some NyQuil right before class, so I was a little foggy headed. I probably should have waited till after class, but I wasn't thinking. So yeah, I don't have it from last class, but this one I'm going to be uploading like very soon. All right.
So in polar coordinates, area and integrals are kind of different.
No, area is an application of integral.
So this is like how you would do an integral on a polar coordinate?
Well, polar coordinates, X or whatever, so forget all of this, just an integral. An integral is an abstract object with no actual meaning at all. It's just a set of rules of how you do something to this thing called a function. So it turns out though, that integrals have applications to geometry for things like volume, area, disk washer, and all of that. So it's like the number, so 5. So in modern life, when somebody says 5 to you, we think of quantity. We think of 5 as 5 things. But in ancient Greek, if you said 5, they would think of a shape. They would think of a pentagram. So a number is just 5, has no meaning. 5 is just 5. But we find things in the world that it can be applied to. So an integral is just a mathematical, logical construction that has no meaning outside of itself. Turns out you can use them to find area. You can use them to find algebra, volume. You can use them to find displacement. So does that make sense? So a hammer is just a physical object that, oh, by the way, I can use it to pound nails into wood. So I think that's what your question was, but I'm not.
Yeah, pretty much. I was thinking like if you found the derivative of this, it would be different than what you started with.
Oh, the derivative of that?
Would be the derivative of this integral would be different than what you started with.
Oh,
Right.
because we're applying an area rule. We're squaring it. We started with a function, but then to do the integral, we squared it. Yeah, you're right. So we wouldn't get back the original function because the formula for, oh, I see what you're saying. So R is 1 minus cosine of 2 theta, right? Well, the derivative of that, R prime, is one thing. The integral of R is another thing. So the integral of this will not give you the area because our area formula is based on sectors, pizza pie slices. When we do the area in polar, our area is 1/2 alpha to beta R squared. So before we even do the integral, we're altering the original function. So if you did the derivative of R squared, you wouldn't get this. You'd get whatever this is squared. Does that make sense?
Yeah, that makes sense. Thank you.
Yeah, you're welcome. Good question. All right. Well, there we go, folks. So it's Thursday. So have a great weekend. I will see you back here on Tuesday. And again, I'm sorry the test grades are so late. I was just kind of like really out of it the last few days. So I'll get them up for you sometime tomorrow. Okay. All right. Bye, everybody. Hey, Kayla. Bye, Kayla. Tonight was our last night of being together on Zoom.